Hello students, in this video I will explain magnetic field strength at a point due to a bar magnet or a magnetic dipole. Here the point can be either on the axis or on the equatorial line of the bar magnet. Let us start with the bar magnet. This is a bar magnet having two poles, north pole and south pole, and the line joining the poles of the magnet is called as its magnetic axis, and the distance between the poles of the magnet is called its magnetic length as shown here. It is a vector which is directed from south to north pole of the magnet, and its length will be represented by 2L. As we have done in electrostatics, that the electric dipole length we have considered as 2L for the simplification in calculations. The distance between the ends of the magnet is called its geometrical length, like it is shown here, and the ratio of the magnetic length to geometrical length is 0.85. Like poles repel each other and unlike poles attract each other. This you all know. The magnetic poles always exist in pairs. The poles of a magnet can never be separated. That is, whenever we are going to break the magnet, again we will form north pole and south pole. Monopole will never be found. As we have done Coulomb's law in electrostatics, here also in magnetism we are having Coulomb's law. It states that the force of attraction or repulsion between two magnetic poles is directly proportional to the product of their pole strengths, and the force of attraction or repulsion between two magnetic poles is inversely proportional to the square of the distance between them. This is known as the inverse square law. So this force from the first statement, it is proportional to the pole strengths. Here we are considering the pole strength as M1 and M2. So force is proportional to product of M1 and M2. From the second statement, force is inversely proportional to square of the distance between the two poles. If we combine above two and remove the proportionality sign, we will obtain a constant, that is mu naught upon 4 pi. If we combine the above two terms, we have obtained mu naught upon 4 pi into m1 m2 upon r square. Mu naught is permeability of free space. Now let us discuss magnetic dipole moment. It is the product of the strength of either pole and magnetic length of the magnet. Here we are considering the length as 2L. So magnetic dipole moment will be equal to m into 2L. If we cut this magnet in two equal parts along its length, then the pole strength is reduced to half and the length remains unchanged. Then what will happen to the magnetic dipole moment? See here, suppose this is the bar magnet having equal pole strengths M. Now I am cutting this magnet in two equal parts along its length like this. So we will obtain two magnets having the same length as the previous one, that is 2L, but the pole strength will reduce to half of each, half of the previous one. So we will obtain the magnetic dipole moment as m by 2, that is half of the previous magnet. Now again let us consider one more case, that if the magnet is cut into two equal parts transfers to its length. Then what will happen? See, this is the magnet. I am cutting the magnet, transfers to its length. That is according along the equatorial line of the magnet. So the length will reduce to half in the two magnets, but their pole strength will remain the same. See here, like this. So now the new magnetic dipole moment will become half of the previous, that is m by 2. Now let us start with the magnetic field strength at a point due to a bar magnet. For this, let us first understand the strength of the magnetic field at any point. It is defined as the force experienced by a hypothetical unit north pole placed at that point. See, we have used the term hypothetical because we know that unit north pole do not exist alone. Poles are always found in pairs. It is a vector quantity, and the direction of the magnetic field is the direction along which this hypothetical north pole would tend to move if it is free to do so. That means the direction of the magnetic field will be same as this hypothetical north pole will move when it is free to do. So the direction of that north pole will be same as the direction of the total magnetic field. Now let us start with it. For this, let us consider a point P on the axial line of the bar magnet. This is a bar magnet having pole strength M here. This is the north pole of the bar magnet. This is the south pole. We have to find the magnetic field at point P, which is at a distance r from the center of the dipole. This is the hypothetical north pole. The bar magnet is having length of 2L, and we will first find the magnetic field due to north pole of the bar magnet, then we will find due to south pole, and later we will calculate the total magnetic field of the bar magnet at point P. For this, magnetic field strength at P due to north pole will be this, that is mu naught upon 4 pi into pole strength upon distance square. Distance will be r minus L. The distance between the north pole of the bar magnet and point P is r minus L. So in the denominator it will be r minus L whole square, and the direction will be away from P. This is the direction. As this is also a north pole, this is also a north pole, so they will repel each other. So the direction will be away from north pole. That means NP produced. Similarly, we will find the magnetic field strength due to the south pole of the magnet. See the distance of the south pole from the point P, it is r plus L. So the magnetic field strength will be mu naught upon 4 pi into m upon r plus L whole square, and the direction will be attractive. See here, this is the south pole, this is a unit north pole, so the direction of this magnetic field will be represented by towards the south pole, that is along PS, as is shown in the figure. So the net magnetic field strength at point P due to the bar magnet will be difference of the two, as both the directions are opposite, and due to north pole it is greater, so it will be B minus B dash. When we will put down the values and simplify, we will obtain this expression. Look carefully, this is m into 2L, which is magnetic dipole moment. So I have kept this as capital M. As we are aware that the length of the bar magnet is very small, that is we have considered a short bar magnet, and the point P is located at a far off distance. So in the denominator we can neglect L square as compared to R square. So we will be left with mu naught upon 4 pi into 2m upon r cube, and its direction will be NP produced. Now, when point P lies on the equatorial line of the bar magnet as shown here. Here we have considered that the bar magnet is having pole strength of M, length 2L, and the point P is at a distance of R from the center of the dipole. We can easily calculate the distance Pn or Ps. It will come out to be R square plus L square under root. Now let us calculate the magnetic field strength at point P due to the north pole of the magnet. As both are north pole, so the direction will be away from the north pole as shown here. And the magnitude will be again calculated by Coulomb's law, that is mu naught upon 4 pi m upon distance square. Here distance square will become R square plus L square. Then we will calculate the magnetic field due to south pole of the magnet. It will come out to be mu naught upon 4 pi into m upon R square plus L square. If we look carefully, the magnitude of magnetic field at point P due to north pole and due to south pole are equal to each other. Let us resolve them into components. This will be the component due to B dash, that is the sine component, and its cos component will be along Px. Now let us resolve the magnetic field obtained due to north pole of the magnet in two components. This will be the sine theta component and this will be the cos component. If you look carefully, the sine components are in opposite directions and their magnitudes are equal, so they both will cancel each other. Hence, the magnetic field at point P will only be dependent upon the cos components, as both the cos components are in the same direction, that is along Px direction, so they will get added up like this. Both the magnitudes B and B dash are equal to each other, hence we can write it as 2B cos theta. Now let us put down the value of B from above, either from here or from B dash equation, both are same. We will obtain, putting down the values, we will obtain this expression. Rearranging the terms, we will obtain m into 2L in the numerator, and it can be rewritten as capital M, that is magnetic dipole moment. Again, we can consider that the magnet is of short length and we can neglect L square from the denominator as compared to the distance of point P, which is R square. So we will be left with this expression, that is mu naught upon 4 pi into m upon R cube. If we compare this expression from the earlier expression obtained at an axial point, we will find that the magnetic field at an axial point is equal to twice the magnetic field at an equatorial point of the bar magnet. Thanks for watching. Please like, share and subscribe.